welcome to the next presentation. This is Tom Field, and Tom, I'm going to let you introduce yourself, talking about spectroscopy and how the mere mortal can actually do it, I guess. Go ahead.
Great. Good evening, everybody, and thank you so much, Drew. And that was a great talk we just heard by Zoe. And I know after me, there's another great talk coming up with Bob Noye. So I hope you'll stick around for that also. So I'm Tom Field. I'm a contributing editor at Sky and Telescope and basically a knuckle-dragging programmer. And what I want to share with you in the next 45 or so minutes is just how easy it is to do the same kinds of things scientists do and capture the spectra of stars. We're going to move pretty quickly here. I give a little bit more leisurely a presentation to clubs. You can find out a little bit more detail about that if you want me to give a talk to your club down at the website listed at the bottom of the screen. So how have we managed to discover so much when we haven't even left home? Images, of course, have always served us well to see deeper into the sky. We can get a fleeting glimpse of a third dimension when we look at eclipses. And if we wait a while, we can see a fourth dimension where things are actually changing up there. Drew, you may want to mute, I think. And you may, if you spread the colors out, you get an as-if fifth dimension. Just aesthetically, this is gorgeous. And in addition to that, it contains an enormous amount of information. You may not be an imager, you may be an armchair astronomer or a visual imager. Regardless of what your interest is in astronomy, you're here, so you have some interest. And I'm going to show you things that will serve you in your understanding, even if you never apply it yourself, in your understanding of all the fantastic things that we've learned over the last several centuries about the astronomical objects we observe. These gaps in a spectrum are like a barcode, and they help us identify various properties of stars. I'm going to show you some examples this evening of these, and then talk about how easy it is for you to do it. Just a little bit of science to get us to the same level. Sir Isaac Newton observed that you can split light in a prism and start with white light and get the component colors. You can also bounce that light off a finely lined surface like that DVD, or even through a piece of glass that's finely lined. It's called a diffraction grating, and that's what we're going to talk about mostly tonight. Bunsen invented his Bunsen burner to study spectra. Drew, your mic's still on. And those spectra allow us to study stars. He kept a wonderful catalog. You can see the era that this was. Kept a wonderful catalog. He'd burn a sample, he'd put it through a prism, and he'd look at the results here. That catalog really served us going forward, as we'll see in a few moments. Kirchhoff was a contemporary of his, and he talked about two different types of spectra. We're not going to get into a lot of detail here. Some of them have gaps, and some of them have bright lines on a dark background. Which you get depends on things we won't talk about this evening, the temperature of the gases involved and things like that. But we're going to see examples of both those. These spectral lines are like fingerprints. Notice that hydrogen here, for example, has a very strong line there that doesn't show up in helium. This would be the helium perhaps that you'd put in a balloon at the florists. So in fact, hydrogen is so common and useful, we've given those lines the name hydrogen bomber lines. And those lines are actually named. So we have, like we named the stars in the constellation by intensity, these are just by position. Hydrogen alpha in the red, this hydrogen beta, that's about what? Robin egg blue and hydrogen gamma. In a minute, we're going to see how we can use those to study the stars with just even like a 4-inch refractor or SCT, or even just a plain DSLR. So if you're imaging today, maybe you're taking wide field DSLR images or imaging planets or deep space objects. This is the kind of thing you'll be really surprised at how easy it is to do. Here's an example of a periodic table that I created a few years ago. We sell it mostly to educators. There, the hydrogen, you can see that hydrogen alpha in red, and there's that robin egg blue beta, hydrogen beta. Notice those lines are very different than the lines of all the other items in the periodic table. They really are these fingerprints that I mentioned. We don't have to burn things like Bunsen did anymore. We now have gas tubes. This gas tube is burning hydrogen. There again is that hydrogen alpha in red, hydrogen beta in that robin egg blue. And in fact, for teachers, we have this little camera here to make observing gas tubes in the classroom for students Really easy to do. It's a fun little product. Uses the same software. We have a lot of universities and high schools using it in chemistry, astronomy, or physics. So far, everybody I've mentioned have been old white men. Let's look at some of the non-old white men. Annie Jump Cannon and her computers, her team of women, were prohibited from accessing telescopes a little more than a century ago because they were women. So they ended up studying the spectrum glass plates, and they observed hundreds of thousands of spectra and came up with just a very insightful and ingenious naming and classification system for the stars. Here we've got Priyamvada Nataraja, who's at Yale studying hyperactive black holes. Nancy Grace Roman was the first astronomer at NASA. She got her PhD in the late 1940s. She was a big proponent of the Space Telescope. Elisa Quintana studies exoplanets, somewhat like we were hearing from Zoe a few minutes ago, where we're looking for evidence of life and various spectral signatures, another way that spectra are used. Jedediah Eisler's at Dartmouth, and she studies gravitational lensing around black holes. We've come a long way, but not long enough or far enough in empowering women in our field, and this is just an example of some of them who have made huge contributions. A little bit more science, and then we'll get into the fun stuff where you can see how it's done, whether you do it or whether other people do it. You may recall the Bohr model of the atom has electrons going around in circular orbits, and when they drop levels, they give off energy. This is a hydrogen electron jumping down to level 2, and you can see it gave off some purple light. Different jumps create different colors. So for example, jumping from 4 to 2 gives us this, well, robin egg blue. That's our hydrogen beta I keep harping on. Now, when an electron drops down, before that can happen, it may have to get pumped up. And if it gets pumped up, we get this gap here, which is an absorption spectrum with a rainbow in the background. So what I'm going to talk about mostly this evening is this little 1.25" grating. It sells for like $200 or so, that you can screw onto almost any camera. You can put it on a DSLR there in the upper corner, you can see. And in my little video preview, we have this little adapter, and you just screw the grating right into the lens cap threads, more or less. With tracking, you can capture really interesting spectra. You can piggyback that DSLR on your telescope or use mechanical tracking. Maybe you've got a FITS camera, color, mono, cooled. In the lower right-hand corner, this is an imaging source video camera. Again, it can be color or mono. Oftentimes, the grating just screws right onto the nose piece. Or you can mount the grating in a filter wheel. So there's lots of ways for you to do this with almost any equipment you've got. There are higher resolution devices. They're considerably, like an order of magnitude, more expensive and much more difficult to use, because now you're acquiring and guiding your target through like a 10 or 20 micron, that's 20 millionths of a millimeter, or of an inch, excuse me, meter, we'll get that right, slit. So enough history and theory and equipment. What can you actually do? That's the fun of all this. Well, you take the light from a star, you put it through a grating, through any of those telescopes and cameras, you capture the results. Here's our first example. This is remarkable. These are all different spectra captured by Torsten Hansen with just an 8-inch Newtonian and an imaging source, a video camera, much like the ZWO camera, a little older. So notice the differences. These stars are in temperature order. So the hot stars are here, the B stars. And then as we go down, they get cooler down to the type K and M stars. Look at the differences. I mentioned earlier there was a bullet that talked about star temperature. Clearly, the hot stars at the top have different lines than the cool stars at the bottom. You don't have to be an astrophysicist to do this. You're going to hear me talk a lot about theoretical issues tonight, but I assure you, I'm like a really broad river that's really shallow. You read as much as you want, and with the web, it's easy to find answers. 2 quick examples here. Notice those wide bands down on these cool type M stars. In fact, those aren't lines. Those are like a forest, right? That's a complex molecule. It happens to be titanium oxide, but I couldn't tell you anything more about them. Titanium oxide that can survive in the outer shell of that star because it's relatively cool. The other example on the screen is, look at this region here in the robin egg blue. This is our hydrogen beta line from that star dropping from 4 to 2. Notice how much more prominent it is here on this type A star, like Vega. Remember, these are being created as electrons jump or drop. And in order to drop, they have to jump first for up to level 4. Well, some of the electrons are so energetic, they go right past level 4 up to a higher level or out. That's these hot stars. Less prominence on this line because there aren't as many electrons to drop down from level 4 to 2. These cool stars down here have less or no evidence of hydrogen because a lot of their electrons never get pumped up high enough to level 4 to drop down. So now, you know, my wife talks about dressing for success, so I think it's important here to honor her wishes. I don't think this is what she had in mind. Here's our hydrogen alpha there in the red, and I know some of you at home, whether yourselves or your partners, you're going to know what I'm talking about when I say I've been having trouble getting the salon to pick up the phone. If you look down in here, it's not all red. I wish it was, but you get down there and it's starting to get a little gray down there. We're all about color and spectroscopy, but that gray is not what we want. And like I said, some of you may have experienced this at home yourselves. So, you know, you see that crosshairs there. It's not enough just to say, gee, it looks like there's a little dimming in there. We need to be quantitative to be doing science. And the way we do that is we create an intensity graph. So the star here is really bright and narrow. So in intensity, in that axis, this peak is very high and not very wide. Whereas this is here dim and it gets brighter, 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 and then dimmer, dimmer, dimmer. So this is dim, brighter, 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 dimmer, dimmer, dimmer. But look at this. That little bit of dimming there is so clear in that graph. That's now science. Now we can measure the full width half maximum, the position, how's it compare to other instruments, to other stars, to other galaxies. And this is something you can produce. So my story is I wanted to do spectroscopy. So in 2009, I got a grating and I went outside right in my backyard through that window here in Seattle, 3 miles from Pike Place Market. I set my C8 up on Saturday night in August. I came in 3 hours later, my neck hurt, my knees on my blue jeans were grass stained because it was Vega in August. What do you expect? The next morning, I tried to create this graph. This literally is the spectrum I captured that first night. I've got it over here. I didn't intend to show you, but it's sort of fun. Here's what it was. It was just some cheap webcam. You can still see the duct tape I used to attach it to my C8. I tried to create that graph using some of the shareware that was out there, and I failed. It was just too buggy, hard to install, and half it was in French, and there was really no documentation. I gave up. I told my wife, this is supposed to be fun. It's a hobby, right? And I can't get it to work. I'm a little embarrassed to say I quit. I gave up, but it kept bugging me. So about 2 weeks later, I said, okay, Saturday after my work week, I'm going to create a program to create this graph so I can see those dips and detect elements on stars affecting the light that's coming to the Earth, you know, millions of light years away, perhaps. So Saturday I wrote it. It was done Sunday. And now 10, 11 years later, I'm almost done the software after 10 or 15,000 hours worth of programming. I think one of the big obstacles we all face when moving into something new is, oh no, I'm going to have to learn a new piece of software. So I want to show you that it's really not a big deal to capture spectra using the RSpec software. Here's an image. I prefer color when I'm doing outreach or education because it's more intuitive. There's the star, there's the spectrum from my first night out. This is a single frame. So this could be a FITS image. It could be mono. So all you do is bracket it in with these orange lines, the area you want to study, and you see that intensity graph. There's the peak of the star. And look, there's a little gap there. There's that gap there in the data. Big deal, right? It's gaps. What does it mean? That's really the challenge. The devil's in the details. So remember I mentioned Bunsen kept a catalog. Well, the great grandchildren of that catalog still exists and is used. And here's an example of it in the software. So we can come up here to Hydrogen Bomber and say, show me on the graph where there would be dips if there had been hydrogen on the star, this is Vega, affecting the light as it left the star. And look, we've got matches for that hydrogen alpha line, beta, gamma. This is with an 8-inch SCT and a video camera in Seattle itself. So the nice thing about spectroscopy is it's not nearly as affected by urban light pollution. We're not so concerned about aesthetics or color balance. We want the data that hits our sensor to be the data that we study. So it's one of the kinds of things you can do on a full moon night or, from the city instead of driving out to a dark sky site. So now for outreach, this is a fantastic screen. We can gussy it up with a little color. And I'm actually going to play a video. This is the original video at 2 frames a second that I recorded. The star and the spectrum are jumping around here for my local seeing, and here it is jumping around there. So that's what I wanted to show you in the software. Notice that these dips, like this hydrogen alpha dip, is coming and going. So what we can do is turn on stacking in the software. Watch how quickly that dip there becomes visible. At 2 frames a second, it just took like 10 or 15 frames. That's the beauty of stacking, which isn't necessary to do this, but it can improve your images. So having shown you that, what I'd like to do now is I'm going to pause that playback and go back to the PowerPoint. Here's a great example of the kinds of public outreach you can do on the sidewalk at a high school. You can go into a high school now with this kind of tool, which is really easy to learn. And you can work with a science teacher and mentor students on doing this themselves. You help them with a telescope, you help them understand how to capture spectra, and they win science fairs perhaps. Or if nothing else, they learn a lot, and you have the pleasure of having facilitated that. So here's a spectrum, a wide field spectrum with a DSLR. There's some stars. There's a gap in the spectrum. Here's a star here. There's some lumps, right? Those are emission lines that are being caused by this Wolf-Rayet star. Now, I have a confession to make. When Janet Simpson in the UK sent me this DSLR image, by the way, do you feel like you're drinking from a fire hose? Like I said, I have a little bit more lengthy and leisurely presentation I give to clubs, but I wanted to squeeze this all in. I have stripped a fair amount out, but my confession is that I couldn't remember what a Wolf-Rayet star was. I'd read about them over the years, but things go in one ear and out the other unless we have some relationship to them. And when you own the data, when you have it in hand and it's your own data, things start to be a lot more interesting. If it was hard to capture, I wouldn't be recommending it. Who wants to be out in the cold this winter? For those of you in the northern area of the country, like me in Seattle, I'm not only cold, but I'm wet here in Seattle. But this is the kind of thing that's so easy to learn. And it just brings so much reward because, well, Wikipedia is your friend on Wolf-Rayet stars. And so let me just get my mouse cursor visible here again permanently. Thank you, Microsoft, for not making that sticky, so I have to do it every time I leave the screen. Wolf-Rayet stars are really massive stars at the end of their life. Maybe they're headed to be a supernova. They're dissipating their outer shell with really intense stellar winds, and we can actually see, into a little bit of the star, and what we see is emission lines. Carbon, carbon, carbon. Why would we see carbon? Well, remember, stars are burning their way through the elements, and carbon is one of the things that they burn through as they begin to exhaust their fuel. And we're seeing it here with a 30-second DSLR exposure and mechanical tracking, as it says there at the caption at the bottom. So this is an emission object. Let's look at another emission object, the Ring Nebula, our beloved Ring Nebula, right? There's its spectrum, and notice we can see 2 different chemicals there, or emission lines, hydrogen alpha and ionized oxygen. That's what that Roman numeral 3 means. If you're not familiar with it, it just means ionized. Some of the electrons have been moved away or pulled up. So most extended objects don't have an interesting spectrum like this. This is extended, right? It's not a point source. For those, you really need to use one of those slit spectrometers. And here's an example of an extended object, right? But with a slit spectrometer. There's our hydrogen alpha that we saw glowing in the previous Wolf-Rayet, and there's our ionized oxygen with that Roman numeral 3. So, and lots more detail. So for me, the first time that I saw the Orion Nebula was the first time I went to a star party in the early 1990s. It's fun to remember when you didn't know something. I walked out on the observing field, and maybe you had a similar experience. All I saw, you know those cannons that they shoot people out of at the circus? That's what I'm thinking, what is that? Well, I didn't know they were Dobbs. I queued up. Somebody like many of you perhaps, or me, was running the Dobb, explaining. We were looking at the Orion Nebula. I was all excited. I'd seen those pictures in the magazines, and I got up and I was really disappointed. It was a smudge. It was nothing. But I still go back and look at M42 today. Why would I do that? Well, I'm in dark sky sites and I have better equipment. And yeah, we all know a little bit more about using averted vision where we can look at things, out of our peripheral vision when they're a little dimmer. But more importantly, the reason that I still go back, and I bet you do, is you understand a little bit more about what we're seeing. It's a stellar nursery. Stars are being born. My point of telling that story is when we have a deeper understanding of the science behind what we're observing, and that's what spectroscopy brings, our visual observing and our visual imaging gets that much more interesting. In 1881, Henry Draper, that's that Draper catalog guy, observed the spectrum of a comet. If Hank can do it, so can we. There's the spectrum. There is the graph, some really nice swan bands of carbon. This was captured by a guy named Vikram Agnihotri. He's in Northwest India. He's a nuclear power plant engineer. In 2013, he was a beginner, and now he's an expert. I learned from him. And what teacher doesn't want to learn from their student? So here's a more contemporary example of Neil Wise's tail, and we're observing with this is really a cool spectrum. It's just with the DSLR and the grating screwed onto it. It's called an objective grating. So that's the kind of thing that you can do. Anybody who uses a webcam and a C-clamp, now they're my kind of amateur, but the problem is if I was, using that C-clamp, I'd crank it down too tight and I'd break the enclosure and break the camera. Fortunately, Robin Leadbeater was more easy-handed, more gentle than I am. He put a star analyzer grating on the video camera, and he designed the star analyzer grating, and he's on our online forum, and he helps lots of us. He's an expert and a really great guy. He captured a frame here, and in that frames period of that video, a single frame, the meteor moved that distance. Here's its spectrum over here. That gap, for example, right there is that dip. And you can see he was able to actually observe some of the material, some of the composition of that comet. It's a rather esoteric field. You've got to find, not comet, meteor. You've got to find these objects first, and they're not that common, as you know. We're not going to talk much about the sun since we've heard so much about it over the last several years, and will be again in the next several years, except to point out that we observed helium on the sun with that yellow line before we had any idea it was here on Earth. It's an amazing story. I'm sorry we don't have time to tell it tonight. You can observe novae. Some have iron evidence, some don't. For example, just with a DSLR. A quick review, Doppler shift. Basically, if something's coming towards you, the sound and light, any wave that's emanating from it is going to be higher pitched. So, for example, the train going through a station, the whistle as it's coming through, high, low, right? Same thing, right? High is when it's coming towards you, low is when it's moving away. Same thing with light. So if we were expecting this triplet here, I love that word, it's self-defining. If we were expecting a triplet here, and when we captured the spectrum, it was really over to the side. We know that it was redshifted, so it was an object that was moving away from us because the waves were spread out like these waves behind the car. Same thing, if it was shifted the other direction, we know it was blue shifted and it was moving towards us. Here's a wonderful example. An exploding supernova. There are lots of different types of supernovae. We're going to look at a type called type 1A. Without getting into the details, a binary pair, a pair of stars, and one of them is larger and dumps some gas somehow onto the smaller one. And when you pour gas on a hot surface, what do you get? You get an explosion. So here's a supernova in M101. There's a photograph of another supernova. It's not this one, but it is the same type, a type 1A. Look, you can see that sphere of the explosion.
So there's the spectrum that David Strange was able to capture with just 15 minutes of stacked images on a 9-inch SCT. Here's the spectrum he got. And look right here, that little dimming you see in that deep dip. So, we talk about standing on the shoulders of giants. Imagine as an amateur, we could do this kind of thing. And we can with such simple gear. So I'm not showing you examples here of like the best of amateur astronomers. These are rank and file people like you and I are. And they're able to do this really easily. So the giants have classified supernovae. Now this won't be on the quiz, but I want to show you for this type 1a, this 2 stars of, circling one another. Notice that deep dip right around 6,000. But none of these other supernovae, like when they run out of fuel and collapse on themselves, none of them have a deep dip in the silicon there. They have other unique features, like, for example, this one or that one. But when we see that deep dip around 6,000, that's how we and David Strange were able to identify this as a type 1a supernova. And that's the kind of activity that some amateurs choose to do to help out identify new supernovae. They're usually pretty dim, so you need fairly big aperture. I don't want to make that part sound more easy than it is. But look what we did. We noted the wavelength of that feature, that dip, and we wrote it down. Then we noted using, if Bunsen had burnt beach sand, he would have found it, that deep dip at that wavelength. They're different. So I couldn't remember the Doppler Shift formula. Wikipedia is your friend and mine. And when I threw the numbers in, we were able to calculate the blue shift from that shell expanding and coming towards us at such an enormous velocity with a backyard telescope. Now, Adam Rees and his team, right before the turn of the century, were studying the accelerating cosmological expansion, and they used type 1a supernovae to detect some of that expansion. And somehow I think they use something a little more sophisticated than our star analyzer grating. But to be able to reproduce that kind of thing is so exciting for many of us. So what about the spectrum of a black hole? Well, a black hole, of course, itself doesn't emit any light, but the matter that's spiraling in gets very hot and emits light. So David Hayworth observed a quasar. There it is. I've never looked at this myself. And there you can see the spectrum with 2 little dots of light. There they are. There's the spectrum. Now, this guy, Martin Schmidt, was in his mid-20s in the 1960s. He stared at this and he wanted to figure out, what are those peaks? We can't even see them in the spectrum visually, but they're very clear in the graph, aren't they? So he got a little frustrated. He decided to go back to square one. And for that, what he did was he said, I'll put up the reference lines for the hydrogen bomber series to prove these aren't hydrogen bomber. Let's eliminate what they aren't. So this is a screen from my software. The point being, in fact, the software you just saw demoed, you can see those hydrogen bomber reference lines. There's a hydrogen alpha there, and the robin egg blue is the beta. But they don't really line up, do they? There's no big peak here that matches something, a blue line here. So he was able to conclude, well, they're not hydrogen, except they were, and he figured it out. Enormously redshifted. And that meant that this object was a really long ways away using the Hubble constant. The discovery was that it could be that far away, so enormously far away and still bright enough for us to see it. So, and the amazing thing to me is that light that has traveled so far, that is so ancient, still has information in it that we can study ourselves with simple equipment and learn something about the way that object was billions of years ago. Light doesn't seem to age. Humans age a little more quickly, don't they? I've been justly accused of, throwing rocks in a glass house. He's got a full head of hair and I don't. So it's really more envy that I show you this photo. So 2 more quick examples and we'll finish up. So far, we've been looking at features like these hydrogen bomber features and some others. What if we wanted to look at the detail in this hydrogen alpha feature, that dip? We can't just use our mouse roller wheel, right, to zoom in. I mean, because there's only so much information there. That would be like, well, for example, think about when you're observing the moon. I mean, it's tempting, and we all tried it initially. Just put in more magnification with a higher mag eyepiece. Eventually, it's empty magnification, right? In order to really get data, you need more sophisticated equipment. So what we do is, this is where we use a slit spectrometer. Look here, the moon is in blue and Vega is in fuchsia. Notice that hydrogen alpha dip, this is that region, but this is one of those more expensive, difficult to use slit spectrometers. But I want you to see this example. Here we can detect the radial velocity of Vega because it differs from the moon, which the moon isn't really moving towards or away from us very much, but clearly Vega is. Last example, and that is this rapidly rotating star. I need to become a Harlem Globetrotter so I can entertain you with this on my finger. So this is rotating very quickly. This edge is coming towards you, right? So that light is going to be, I can never remember, blue shifted. And this light is going to be moving away from you as it leaves the star. So that's red shifted. And the light here isn't really shifted much on account of the star's rotation, right? This surface isn't really moving that fast towards or away or at all. So what we expect would be some of the light that would normally be here is going to be spread out into the red. And some of the light that would normally be here is going to be sort of stolen and spread out into the blue. And here's what that looks like. See that broadening and lack of sharpness in the dip for Vega, for Altair in blue versus Vega? This is rotational broadening. This also requires a slit spectrometer, but this is the kind of thing that amateurs can do. So I've shown you a lot of examples just now. Not that there's not going to be a quiz, but I'd like you to come away going, that's not so hard. And how do you get started if you'd like to try it? Well, you need a grating like our star analyzer grating, which I mentioned. It's about $200. You need almost any sort of camera that you're using today, or you can pick up a video camera, which can double as a really fun planetary camera too, for a few $100s. This is the ZWO 178. You may need a spacer or adapter because it's not critical. See if I can do this without dropping something. This distance, I need like another hand. I need to be an octopus. The distance from the sensor to the grating, it just can't be too long or too short. And so there's a calculator on our site that helps you figure that out. And as you may have gathered, I love helping people. I spend a lot of time where potential, amateurs, they just say, here's my telescope, here's my camera, what do I need to get started? And I figured it out and I just send an email back and you're good to go. You also need software. This is my software, RSpec, which stands for real-time spectroscopy. I showed you an example of that you could use at a dark sky site or, in the city. I've set my laptop up on the hood of my car outside the portico at a Holiday Inn where there's a professional conference, with like a 6-inch refractor. And these professionals come out. I'm always a little embarrassed at first. I go, hey, you want to look at Vega? These are people who are using Hubble, but they've never seen a spectrum captured live. And so they come over like, yeah, okay, we'll humor this kid. Somehow I feel like a kid when I do that. And do we ever grow up? So, and then they get interested. And whether it's a professional or high school students or the public, it's wonderful for outreach. This is the shareware I mentioned earlier. It's grown a lot. It's a really powerful software. It still has some of the challenges that I experienced learning curve-wise and usability-wise, but great software. So how do you go further in identifying spectra? Well, the cool thing is there's lots of books. They're all linked to on my site. You can always email me at the contact form on our site if you've got a question. That book on the right there, I wanted to show you just 2 quick examples. Look at that. There's a spectrum that's all annotated, and the annotations aren't good enough for me. A knuckle-dragging programmer that I am, I go, ionized nitrogen. What does that mean? But the book also has a lot of prose that explains what we're seeing. And this is written for us, for amateurs, not for postdocs or people who are, studying this in college. So the software is free for 30 days. The AVSO now has a Spectra database. They're jumping deeply into spectroscopy. Stella Kafka, their great director, and her predecessor, Arnie, they're professionals. They know how important spectroscopy is. There's a database in France. There's one in the UK. In fact, I gave a workshop to the AVSO members, and it was about 100 people live 4 years ago. And it was recorded. It's on YouTube. This page on my site links to the YouTube video, the sample data that the attendees to the workshop used on their laptop, and I go through step by step, much like my on-site tutorials do. There's no big, thick manual to read with this stuff. It's really a lot easier than some of the things you've probably done already. So you can download the software and tomorrow morning be playing, whether you ever did this with your telescope or real data, doesn't matter. But if you did it for an hour or two, you'd have it in your bones. You really would. That's how we learn. So there are pro-am opportunities, more coming day by day, and you'll see more of that in an AVSO workshop coming up. I think I dropped a syllable there. Workshop coming up in November. So we've come a long ways in the last 40 minutes and the last 200 or 300 years. To me, it's always remarkable the accomplishments of humanity, starting out with nothing but a prism, and now we're understanding stars that are so distant. And a lot of that research gets done with spectroscopy. It's great to understand. It's even more fun to do it. I'd like to thank the organization, Kopernik, for inviting me tonight, and all of you for hopefully smiling at some of my jokes. I'm going to stop sharing my screen, and we'll have a little time for Q&A. And like I said, you can always send me an email or use our contact form on the site. I love answering questions. Thanks again. You're muted.
Yeah, I should know better than that. Anyway, thank you so much, Tom. I really appreciate it. It's clear that this COVID thing has really knocked you down. I can't imagine what you must be like.
Hey, Tom. Hi, Drew.
Hey, we thought we'd surprise you here with Bob.
Oh, Bob Noye.
How's it going? Bob? You know, it's amazing. You showed Priya Natarajan. I was emailing her just about 2 hours ago.
Really?
Yeah.
Wonderful. Well, and in fact, one of the slides I showed, the Adam Rees slide, you also emailed me, or you emailed him about my cosmological expansion, because I call it Doppler Shift. Sometimes I tell this story when I have fun.
Okay.
And he said, Adam Rees, is this Doppler Shift? And you knew the answer. You just wanted backup from me, I think. And he said, no, it's not Doppler. Cosmological expansion, nothing's moving.
That's right.
Yeah. Way to think about things.
Yeah.
Nice to see you, Bob. It's been a while.
Yeah, I enjoyed I missed the last couple of minutes of your talk because I was, logging in using Zoom rather than YouTube, and I didn't want any sound or anything, but I caught most of your talk and really enjoyed it.
You could give this talk, Bob, and in fact,
you know way more about. And my talk though does have spectroscopy in it.
Oh, good. I'm looking forward to it.
Yeah, it has some spectroscopy in it.
Good. Well, thank you again, Drew. I appreciate it. If there are any questions, I see Leanne. Thanks for your applause. And I'm hoping that we get a chance to meet all of you at NEAF sometime in the future.
Yeah, I thought I'd seen it. Well, thanks. At this point, again, you seem to have whatever questions people have, you seem to have maybe answered them, but. It's also great to know that just again with even some modest equipment, you can do some really fun things, and I think that's certainly one of the things that we here at Kopernik trying to do is just make people aware that the science and engineering is really can be accessible to people, and so you got to take that first step. And you got to play around, and then you got to start connecting with other people. We end up helping each other out. One of my hobbies actually is ham radio, and I've been a ham for over 50 years, and I still learn things from other hams, and so it's this. I think we all just need to get into this lifelong learner kind of format here. Let's see what else we got here.
Hi, Greg. Nice to see you. Greg's a happy user of RSpec. We've actually had a chance to meet a couple times.
Oh, very cool. Very cool. And Dave Jordan's actually a friend of mine down in Florida that also a ham operator, and Oh, I got your NASA shirt there. Great. Okay, thank you much.
I was going to wear a Hershey Bears shirt, but that would annoy Patrick. Binghamton fan.
Yeah, that's one of the nice things also is that again, this ends up being a relatively I want to say small group of friends, but it's people that know each other, and so we get to know each other's idiosyncrasies and which teams they like and which teams they hate, and so.
Well, thank you again, Drew, and I look forward to Bob's talk, and thank you for putting this together. I think that it's a real benefit to the extended community.
Well, you're so welcome. You're so welcome. Really appreciate it.